are likely places for an embolism. A piece of a thrombus that breaks loose, called an embolus, is likely to travel to and become lodged in a vessel of smaller diameter, blocking its flow and embolism. Arteries already narrowed by plaque formation are likely places for an embolism. An embolism in an artery in the brain causes the cells fed by that artery to die. This event is called a stroke. The specific damage resulting from a stroke, such as memory loss, speech impairment, or paralysis, depends on the location of the blocked artery. The specific damage resulting from a stroke, such as memory loss, speech impairment, or paralysis, depends on the location of the blocked artery. The most effective approach to cardiovascular disease is prevention by healthy lifestyle choices, not treatment. Probably the most important determinants of whether or not you will get atherosclerosis are your genetic predisposition and your age. Environmental risk factors also play a large role. However, if you do have a genetic predisposition to atherosclerosis, it is even more important to minimize environmental risk factors. These factors include high fat and high cholesterol diets, smoking, and a sedentary lifestyle. Certain untreated medical conditions, such as hypertension, high blood pressure, obesity, and diabetes, are also risk factors for atherosclerosis. Changes in diet and behavior can prevent and reverse early atherosclerosis and help fend off the silent killer. The electrocardiogram. The electrocardiogram (ECG) is a continuous record of cardiac electrical activity obtained by placing sensing electrodes on the surface of the body and recording the voltage differences generated by the heart. The equipment amplifies these voltages and causes a pen to deflect proportionally on a paper moving under it. This gives a plot of voltage as a function of time. The ECG records the dipoles produced by the electrical activity of the heart. To understand the ECG, it is necessary to understand the behavior of electrical potentials in a three-dimensional conductor of electricity. Consider what happens when wires are run from the positive and negative terminals of a battery into a dish containing salt solution. Positively charged ions flow toward the negative wire. Negative. 20 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Pole and negatively charged ions simultaneously flow in the opposite direction toward the positive wire. Positive pole. The combination of two poles that are equal in magnitude and opposite in charge and located close to one another is called a dipole. The flow of ions current is greatest in the region between the two poles, but some current flows at every point surrounding the dipole, reflecting the fact that voltage differences exist everywhere in the solution. Measurement of the voltage associated with a dipole. What points encircling the dipole in figure 15 have the greatest voltage difference between them? Points A and B do because A is closest to the positive pole and B is closest to the negative pole. Positive charges are drawn from the area around point B by the negative end of the dipole, which is relatively near. The positive end of the dipole is relatively distant and, therefore, has little ability to attract negative charges from point B, although it can draw negative charges from point A. As positive charges are drawn away, point B is left with a negative charge or negative voltage. The opposite happens between the positive end of the dipole and point A, leaving with a net positive charge or voltage. Points C and D have no voltage difference between them because they are equally distant from both poles and are, therefore, equally influenced by positive and negative charges. Any other 2 points on the circle, E and F, for example, have a voltage difference between them that is less than that between A and B and greater than that between C and D. This is also true of other combinations of points, such as A and C, B and D and F voltage differences exist. In all cases and are determined by the relative influences of the positive and negative ends of the dipole. RPT-15 creating a dipole in a tub of salt solution. The dashed lines indicate current flow. The current flows from the positive to the negative poles portions of the ECG are associated with electrical activity in specific cardiac regions. We can use this analysis of a dipole in a volume conductor to rationalize the waveforms of the ECG. Of course, the actual case of the heart located in the chest is not as simple as a dipole in a tub of salt solution for 2 main reasons. First, excitation of the heart does not create one dipole. Instead, there are many simultaneous dipoles. We will focus with the net dipole emerging as an average of all the individual dipoles. Second, the body is not a homogeneous volume conductor. The most significant problem is that the lungs are full of air, not salt solution. Despite these problems, the model is useful in an initial understanding of the generation of the ECG. At rest, myocardial cells have a negative charge inside and a positive charge outside the cell membrane. As cells depolarize, the depolarized cells become negative on the outside, whereas the cells in the region ahead of the depolarized cells remain positive on the outside. Figure 6. Dipoles. We will focus with the net dipole emerging as an average of all the individual dipoles. Second, the body is not a homogeneous volume conductor. The most significant problem is that the lungs are full of air, not salt solution. Despite these problems, the model is useful in an initial understanding of the generation of the ECG. At rest, myocardial cells have a negative charge inside and a positive charge outside the cell membrane. As cells depolarize, the depolarized cells become negative on the outside, whereas the cells in the region ahead of the depolarized cells remain positive on the outside. Figure 16. When the entire myocardium is depolarized, no voltage differences exist between any regions of myocardium because all cells are negative on the outside. When the cells in a given region depolarize during normal excitation, that portion of the heart generates a dipole. The depolarized portion constitutes the negative side, and the yet to be depolarized portion constitutes the positive side of the dipole. The tub of salt solution is analogous to the rest of the body in that the heart is a dipole in a volume conductor. With electrodes located at various points around the volume conductor, i.e., the body, the voltage resulting from the dipole generated by the electrical activity of the heart can be measured. Depolarization in progress. Endocardium veins epicardium. Depolarization complete. Direction of ARIG. Aerization cardiac dipoles. Partially depolarized or repolarized myocardium creates a dipole. Arrows show the direction of depolarization or repolarization. Dipoles are present only when myocardium is undergoing depolarization or repolarization. Consider the voltage changes produced by a 2-dimensional model in which the body serves as a volume conductor and the heart generates a collection of changing dipoles. Figure 17. An electrocardiographic recorder, a voltmeter, is connected between points A and B. Lead I. See below. By convention, when point A is positive relative to point B, the ECG is deflected upward, and when B is positive relative to A, downward deflection results. The black arrows show in 2. Institute for Advanced Studies, Jodhpur 21. Unit 7 System Physiology Animal. Dimensions the direction of the net dipole resulting from the many individual dipoles present at any one time. The lengths of the arrows are proportional to the magnitude voltage of the net dipole, which is related to the mass of myocardium generating the net dipole. The colored arrows show the magnitude of the dipole component that is parallel to the line between points A and B. The recorder electrodes this component determines the voltage that will be recorded. The P wave and atrial depolarization. Atrial excitation results from a wave of depolarization that originates in the sonoid and spreads over the atria, as indicated in panel 1 of figure 17. The net dipole generated by this excitation has a magnitude proportional to the mass of the atrial muscle involved in a direction indicated by the solid arrow. The head of the arrow points toward the positive end of the dipole, where the atrial muscle is not yet depolarized. The negative end of the dipole is located at the tail of the arrow, where depolarization has already occurred. Point A1, therefore, positive relative to point B, and there will be an upward deflection of the ECG as determined by the magnitude and direction of the dipole. Once the atria are completely depolarized, no voltage difference exists between A and B, and the voltage recording returns to 0. The voltage change associated with atrial excitation appears on the ECG as the P wave. The PR segment and atrioventricular conduction. After the P wave, the ECG returns to the baseline present before the P wave. The ECG is said to be isoelectric when there is no deflection from the baseline established before the P wave. During this time, the wave of depolarization moves slowly through the AV node, the AV bundle, the bundle branches, and the Purkinje system. The dipoles created by depolarization of these structures are too small to produce a deflection on the ECG. The isoelectric period between the end of the P wave and the beginning of the QRS complex, which signals ventricular depolarization, is called the PR segment. The P wave plus the PR segment is the PR interval. The duration of the PR interval is usually taken as an index of AV conduction time. The QRS complex and ventricular depolarization. The depolarization wave emerges from the AV node and travels along the AV bundle of its bundle branches, and Purkinje system. These tracks extend down the interventricular septum. The net dipole that results from the initial depolarization of the septum is shown in panel 2 of figure 17. Point B is positive relative to point A because the left side of the septum depolarizes before the right side. The small downward deflection produced on the ECG is a Q wave. The normal Q wave is often so small that it is not apparent. The wave of depolarization spreads via the Purkinje system across the inside surface of the free walls of the ventricles. Depolarization of free wall ventricular muscle proceeds from the innermost layers of muscle subendocardium to the outermost layers subepicardium. Because the muscle mass of the left ventricle is much greater than that of the right ventricle, the net dipole during this phase has the direction indicated in panel 3. The deflection of the ECG runs upward because point A is positive relative to point B, and it is large because of the great mass of tissue involved. This upward deflection is the R wave. The last portions of the ventricle to depolarize generate a net dipole with the direction shown in panel 4. Point B is positive compared with point A, and the deflection on the ECG is downward. This final deflection is the S wave. The ECG tracing returns to baseline as all of the ventricular muscle becomes depolarized and all dipoles associated with ventricular depolarization disappear. The Q, R, and S waves together are known as the QRS complex and show the progression of ventricular muscle depolarization. The duration of the QRS complex is roughly equivalent to the duration of the P wave, despite the much greater mass of muscle of the ventricles. The relatively brief duration of the QRS complex is the result of the rapid, synchronous excitation of the ventricles. Figure 17. The SEQE of major diff giving rise to ECG waveforms. The black arrows are vectors that represent the magnitude and direction of a major dipole. The magnitude is proportional to the mass of myocardium involved. The direction is determined by the orientation of depolarized and polarized regions of the myocardium. The vertical dashed lines project the vector onto the AV coordinate, It is this component of the vector that is sensed in recorded colored arrow. In panel 5, the tail of the vector black arrow shows the ectopolarized region of the myocardium negative, and the head points to the repolarized region positive. The last areas of the ventricles to depolarize are the first to repolarize, i.e., repolarization appears to proceed in a direction opposite to that of depolarization. The projection of the vector colored arrow for repolarization points to the more positive electrode A as TL to the less positive electrode B, and so an upward deflection is recorded on this lead. The ST segment in phase 2 of the ventricular action potential. The ST segment is the period between the end of the S wave and the beginning of the T wave. The ST segment is normally isoelectric, or nearly so. This indicates that no dipoles large enough to influence the ECG exist. Because all ventricular muscle is depolarized, that is, the action potentials of all ventricular cells are in phase 2, figure 18. 22 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. The T wave and ventricular repolarization. Repolarization, like depolarization, generates a dipole because the voltage of the depolarized area is different from that of the repolarized areas. The dipole associated with atrial repolarization does not appear as a separate deflection on the ECG because it generates a very low voltage and because it is masked by the much larger QRS complex that is present at the same time. Ventricular repolarization is not as orderly as ventricular depolarization. The duration of ventricular action potentials is longer in subendocardial myocardium than in subepicardial myocardium. The longer duration of subendocardial action potentials means that even though subendocardial cells were the first to depolarize, they are the last to repolarize. Because subepicardial cells repolarize first, the subepicardium is positive relative to the subendocardium. See figure 16. That is, the polarity of the net dipole of repolarization is the same as the polarity of the dipole of depolarization. This results in an upward deflection because, as in depolarization, point A is positive with respect to point B. This deflection is a T wave. See panel 5, figure 17. The T wave has a longer duration than the QRS complex because repolarization does not proceed as a synchronized, propagated wave. Instead, the timing of repolarization is a function of properties of individual cells, such as numbers of particular K channels. The QT interval. The QT interval is the time from the beginning of the QRS complex to the end of the T wave. If ventricular action potential and QT interval are compared, the QRS complex corresponds to depolarization, the ST segment to the plateau, and the T wave to repolarization. See figure 18. The relationship between a single ventricular action potential and the events of the QT interval are approximate because the events of the QT interval represent the combined influence of all of the ventricular action potentials. The QT interval measures the total duration of ventricular activation. If ventricular repolarization is delayed, the QT interval is prolonged. Because delayed repolarization is associated with genesis of ventricular arrhythmias, this is clinically significant. Plus 1.0 plus. Plus 0.54. MB. 0. Minus 0.5. MB. PR interval QRS ST segment. 1 La, Lieutenant Erla. I111111. 1111. 11 ECG. 111. 11. The timing of the ventricular membrane potential in the ECG. Note that the ST seg met occurs during the plateau of the action potential. Institute for Advanced Studies, Jodhpur 23. Unit 7 System Physiology Animal. C. Respiratory system. Comparison of respiration in different species. Anatomical considerations. Transport of gases. Exchange of gases. Waste elimination. Neural and chemical regulation of respiration. Physical processes of respiratory gas exchange. The respiratory gases that animals must exchange are oxygen, 0, and carbon dioxide, CO. Cells need to obtain O from the environment to produce an adequate supply of ATP by cellular respiration. CO is an end product of cellular respiration, and it must be removed from the body to prevent toxic effects. Diffusion is the only means by which respiratory gases are exchanged between the internal body fluids of an animal and the outside medium, air or water. There are no active transport mechanisms to move respiratory gases across biological membranes. Because diffusion is a physical process, knowing the physical factors that influence rates of diffusion helps us understand the diverse adaptations of gas exchange systems. Air is a better respiratory medium than water. Oxygen can be obtained more easily from air than from water, for several reasons. The EVO content of air is much higher than the O content of an equal volume of water. The maximum O content of a rapidly flowing stream 1 is less than 10 milliliters of O per liter of water. The O content of the air over the stream is about 200 milliliters of O per liter of air. The oxygen diffuses about 8,000 times more rapidly in air than in water. That is why the O content of a stagnant pond can be 0 only a few millimeters below the surface. Even when an animal breathes, it does work to move water or air over its specialized gas exchange surfaces. More energy is required to move water than to move air because water is 800 times more dense than air and about 50 times more viscous. The slow diffusion of O molecules in water affects air breathing animals as well as water breathing ones. Eukaryotic cells carry out cellular respiration in their mitochondria, which are located in the cytoplasm and aqueous medium. Cells are bathed in extracellular fluid, also in aqueous medium. The slow rate of O diffusion in water limits the efficiency of O distribution from gas exchange surfaces to the sites of cellular respiration. Diffusion of O in water is so slow that even animal cells with low rates of metabolism can be no more than a couple of millimeters away from a good source of environmental O. Therefore, there are severe size and shape limits for the many species of invertebrates that lack internal systems for transporting O. Most of these species are very small, but some have grown larger by having a flat, leaf-like body. Still others have very thin bodies that are built around a central cavity through which water circulates. A critical factor enabling larger, more complex animal bodies has been the evolution of specialized respiratory systems with a large surface area for enhancing respiratory gas exchange. High temperatures create respiratory problems for aquatic animals. Animals that breathe water are in a double bind when environmental temperatures rise. Most water breathers are ectothermic, that is, their body temperatures are closely tied to the temperature of the water around them. As the temperature of the water rises, so do their body temperature and metabolic rate. Thus, with rising temperatures, water breathers need more O, but warm water holds less dissolved gas than cold water does. Just think of the gases that escape when you open a warm bottle of soda. In addition, if the animal performs work to move water across its gas exchange surfaces, as fish do, the energy the animal must expend to breathe increases as water temperature rises. Therefore, as water temperature goes up, the water breather must extract more and more O from an environment that is Increasingly O, deficient, and a lower percentage of that O is available to support activities other than breathing. Figure 1. An active fish uses more 0 than an inactive fish. The O consumption of fish increases as water temperature increases. Metabolism of active fish warm water carries less O than cold water. OXYGEN. CONSUMPTION. OF. FI. Figure 1. The double bind of water breathers fish need more O. When the water is warmer, but warm water carries less O than cold water. 0. Availability decreases with altitude. Just as a rise in temperature reduces the supply of O available to water breathers, an increase in altitude reduces the O supply for air breathers. The amount of O in the atmosphere decreases with altitude. One way biologists express the amounts of different gases in air and in water is by the partial pressures of those gases. At sea level, the pressure exerted by the atmosphere is equivalent to the pressure produced by a column of mercury 760 millimeters high. Therefore, barometric pressure, atmospheric pressure at sea level is 760 millimeters of 24 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Mercury Hg. Because dry air is 20.9% O, the partial pressure of oxygen Pg at sea level is 20.9% of 760 millimeters Hg, or about 159 millimeters Hg. That is, the contribution of O alone to the total air pressure is about 159 millimeters Hg. At higher elevations, where there is less air, barometric pressure declines. For example, at an altitude of 5,800 meters, barometric pressure is only half as much as it is at sea level, so the Pg at that altitude is only about 80 millimeters Hg. At the summit of Mount Everest, 8,848 meters, the PO is only about 50 millimeters Hg, roughly a third what it is at sea level. Since the movement of O across respiratory gas exchange surfaces and into the body depends on diffusion, its rate of movement depends on the Pg difference between the air and the body fluids. Therefore, the drastically reduced Pg in the air at high altitudes constrains O uptake. Because of these constraints, mountain climbers who venture to the heights of Mount Everest usually breathe O from pressurized bottles. Carbon dioxide is lost by diffusion. Respiratory gas exchange is a two-way process. CO diffuses out of the body as O diffuses in. The direction and rate of gas diffusion depends on the partial pressure gradient of the gas. The partial pressure gradients of O and Colorado across gas exchange surfaces are not the same. The amount of CO in the atmosphere is extremely low, 0.03%, so regardless of altitude, there is always a steep partial pressure gradient favoring loss of CO by air-breathing animals. Water-breathing animals are much more likely than air breathers to experience high partial pressures of CO in their environments, especially if the water is stagnant, not well aerated, and contains a lot of decomposing organic material. In such an environment, however, lack of O will probably be a more serious problem. In general, getting rid of CO is not a problem for water-breathing animals. Fick's law applies to all systems of gas exchange. All adaptations that maximize respiratory gas exchange influence one or more components of a simple equation called Fick's law of diffusion, which shows how various physical factors influence the rate of diffusion. Fick's law is written LH equals V2QL, where therefore L is a partial pressure gradient. Animals can maximize D for respiratory gases by using air rather than water as their gas exchange medium whenever possible. Doing so greatly increases Q. All other adaptations for maximizing respiratory gas exchange must influence the surface area A for gas exchange or the partial pressure gradient L across that surface area. Adaptations for respiratory gas exchange. Now that we know the physical factors that influence the rates of diffusion of respiratory gases between an animal and its environment, let's take a look at some of the adaptations animals have evolved for maximizing their respiratory gas exchange. They include adaptations for increasing the surface area over which diffusion of gases can occur, maximizing partial pressure gradients, and minimizing the diffusion path length through an aqueous medium. Respiratory organs have large surface areas. Many anatomical adaptations maximize the specialized body surface area A over which respiratory gases can diffuse. External gills are highly branched and folded extensions of the body surface that provide a large surface area for gas exchange with water. Figure 2a. External gills are found in larval amphibians and in many insect species. Because they consist of thin, delicate tissues, they minimize the length of the path L traversed by diffusing molecules of O and CO. Because external gills are vulnerable to damage and are tempting morsels for carnivorous organisms, protective body cavities for gills have evolved. Many mollusks, arthropods, and fish have internal gills in such cavities. Figure 2b. External gills B. Internal gills. Figure 2 gas exchange systems. Large surface areas for the diffusion of respiratory gases are common features of animals. Both external and internal B gills are adaptations for gas exchange with water. Lungs. EQ is the rate at which a gas such as O diffuses between two locations. ED is the diffusion coefficient, which is a characteristic of the diffusing substance, the medium, and the temperature. For example, perfume has a higher D than motor oil vapor, and all substances diffuse faster in air than in water. EI is the cross-sectional area over which the gas is diffusing. E place and P are the partial pressures of the gas at the two locations. EL is the path length, or distance, between the two locations. Scent and trachea T are organs for gas exchange with air. Air-breathing vertebrates also have large surface areas for gas exchange. Lungs are internal cavities for respiratory gas exchange with air. Their structure is quite different from that of gills. Figure 2 sense. Lungs have a large surface area because they are highly divided, and they are elastic so that they can be inflated and deflated with air. Institute for Advanced Studies, Jodhpur 25. Unit 7 System Physiology Animal. The most abundant air-breathing invertebrates are insects, which have a respiratory gas exchange system consisting of a highly branched network of air-filled tubes called tracheae that branch through all tissues of insect's body. Figure 2d. The terminal branches of these tubes are so numerous that they have an enormous surface area. Transporting gases to and from the exchange surfaces optimizes partial pressure gradients. Fick's law of diffusion points to other possible adaptations besides increasing the surface area for gas exchange. Animals can maximize the partial pressure gradients L that drive the diffusion of respiratory gases across their gas exchange surfaces in several ways. E very thin tissues in gills and lungs reduce the diffusion path length L. E breathing actions move the respiratory medium past the environmental side of the exchange surfaces. This process, called ventilation, supplies the exchange surfaces with fresh respiratory medium that has maximum O and minimum Colorado concentrations. These circulatory systems transport respiratory gases to and from the internal side of the exchange surfaces. This process, called perfusion, helps maintain the lowest possible O concentration and the highest possible Colorado concentration on the inside of the exchange surfaces. An animal's gas exchange system is made up of its gas exchange surfaces and the mechanisms it uses to ventilate and perfuse those surfaces. The following sections describe 4 gas exchange systems. First, let's look at the gas exchange system of insects. Then we'll see 2 remarkably efficient systems: fish gills and bird lungs. Finally, we'll discuss human lungs. Insect tracheae. Respiratory gases can diffuse through air most of the way to and from every cell of an insect's body. This diffusion is achieved through a system of air tubes, or tracheae, that communicate with the outside environment through gated openings called spiracles in the sides of the abdomen. Figure 3a, b. The spiracles can open to allow gas exchange, and then close to decrease water loss. B. Tracheae branch into even finer tubes, or tracheoles, intel. They end in tiny air capillaries. Figure 3c. In the insect's flight muscles and other highly active tissues, no mitochondrion is more than a few micrometers away from an air capillary. Some species of insects that dive and stay underwater for long periods make use of an interesting variation on diffusion. These insects carry with them a bubble of air. A small bubble may not seem like a very large reservoir of O, yet these insects can stay underwater for a long time with their small air supplies. The secret has to do with the PO in the bubble. When the insect dives, the air Bubble contains about 80% nitrogen and 20% as the insect consumes the O in its bubble, the bubble shrinks a little. The bubble doesn't disappear. However, because it consists mostly of nitrogen, which the insect does not consume, when the PO in the bubble falls below the PO in the surrounding water, O diffuses from the water into the bubble. The bubble acts as an auxiliary lung, and for these small animals, the rate of O diffusion into the bubble is enough to meet their O demand while they are underwater. Air sacs trachea. Registered. Figure 3. The tracheal gas exchange system of insects. In insects, respiratory gases diffuse through a system of air tubes tracheae that open to the external environment through holes called spiracles. B. The spiracles of a sphinx moth larva run down its sides and are viscous. Ally obvious. C. A scanning electron micrograph shows an insect trachea dividing into smaller tracheals and still finer air capillaries. Fish gills. The internal gills of fish are supported by gill arches that lie between the mouth cavity and the protective opercular flaps on the sides of the fish just behind the eyes. Figure 4a. Water flows unidirectionally into the fish's mouth, over the gills, and out from under the opercular flaps, so that the gills are continuously bathed with fresh water. This constant, one-way flow of water moving over the gills maximizes the PO on the external surfaces. On the internal side, the circulation of blood minimizes the PO by sweeping the O away as rapidly as it diffuses across. The gills have an enormous surface area for gas exchange because they are so highly divided. Each gill consists of hundreds of leaf-shaped gill filaments. Figure 4b. The upper and lower flat surfaces of each gill filament are covered with rows of evenly spaced folds, or lamellae. The lamellae are the actual gas exchange surfaces. Their delicate structure minimizes the path length L for diffusion of gases between blood and water. The surfaces of the lamellae consist of highly flattened epithelial cells, so the water in the fish's red blood cells are separated by little more than 1 or 2 pum. Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. At gill arches under opercular flap. Water flow. Water flow. Gill arch. Each filament is folded into many thin, flat gas exchange surfaces called lamellae. Oxygenated blood leaves. Deoxygenated blood enters 0 diffuses from water into the blood over the entire length of lamella. Blood flow through the lamellae is countercurrent to the flow of water over the lamellae. Oxygenated blood vessel blood. Figure 4 fish gills. Water flows unidirectionally over the gills of a fish. B. Gill phyla. Men's large surface area and thin tissues. Sent blood flows through the lamel. Lay in the direction opposite, left to right, in this depiction, to the flow of water, right to left over the lamellae. The flow of blood perfusing the inner surfaces of the lamellae, like the flow of water over the gills, is unidirectional. Afferent blood vessels bring blood to the gills, while efferent blood vessels take blood away from the gills. Figure 4c. Blood flows through the lamellae in the direction opposite to the flow of water over the lamellae. This countercurrent flow optimizes the PO gradient between water and blood, making gas exchange more efficient than it would be in a system using concurrent parallel flow. Figure 5. Some fish, including anchovies, tuna, and certain species of sharks, ventilate their gills by swimming almost constantly with their mouths open. Most fish, however, ventilate their gills by means of a two-pump mechanism. The closing and contracting of the mouth cavity pushes water over the gills, and the expansion of the opercular cavity prior to opening of the opercular flaps pulls water over the gills. These adaptations allow fish to extract an adequate supply of O from meager environmental sources by maximizing the surface area A for diffusion, minimizing the path length L for diffusion, and maximizing the PO gradient by means of constant unidirectional countercurrent flow of blood and water over the opposite sides of their gas exchange surfaces. A concurrent flow. Percent saturation of lamellae. E. In the countercurrent exchanges, the water is always more saturated than the blood, so that a gradient of 0 saturation exists over the full length of exchange surfaces. Fig. Point 5. Countercurrent exchange is more efficient than concurrent exchange. Bird lungs. Birds can sustain extremely high levels of activity much longer than mammals can, even at very high altitudes, where mammals cannot even survive. Yet the lungs of a bird are smaller than the lungs of a similar-sized mammal. How can this be? Another unusual feature of bird lungs is that they expand and contract less during the breathing cycle than mammalian lungs do. To make things even more puzzling, bird lungs contract during inhalation and expand during exhalation. Birds can sustain extremely high levels of activity much longer than mammals can, even at very high altitudes, where mammals cannot even survive. Yet the lungs of a bird are smaller than the lungs of a similar-sized mammal. How can this be? Another unusual feature of bird lungs is that they expand and contract less during the breathing cycle than mammalian lungs do. To make things even more puzzling, bird lungs contract during inhalation and expand during exhalation. _. Air capillaries carry air from the parabronchus over blood capillaries, where O is absorbed and then out through the parabronchus. Parabronchus. Blood capillary air capillaries. Fig. Point 6. The respiratory system of a bird. The air sacs and air spaces in the bones are unique to birds. B. Air flows through bird lungs unidirectionally in parabronchia. IR. IR capillaries, the site of gas exchange, branch off the parabronchi. The structure of bird lungs allows air to flow unidirectionally through the lungs, rather than having to. Institute for Advanced Studies, Jodhpur 27. Unit 7 System Physiology Animal. Flow in and out through the same airways, as it does in mammals. Thus there is little dead space in bird lungs, and the fresh incoming air is not mixed with stale air. In this way, a high PO gradient is maintained. In addition to lungs, birds have air sacs at several locations in their bodies. The air sacs are interconnected with the lungs and with air spaces in some of the bones. Figure 6a. The air sacs receive inhaled air, but they are not gas exchange surfaces. As in other air-breathing vertebrates, air enters and leaves a bird's gas exchange system through a trachea, commonly known as a windpipe, which divides into smaller airways called bronchi, singular, bronchus. In air-breathing vertebrates other than birds, the bronchi generate trees of branching airways that become finer and finer until they dead end in clusters of microscopic, membrane-enclosed air sacs, where gases are exchanged. In bird lungs, however, there are no dead ends. Air flows unidirectionally through the lungs. Figure 7. In bird lungs, however, there are no dead ends. Air flows unidirectionally through the lungs. Figure 7. Experiment. Question. How does air flow through a bird's respiratory system? Method. Place oxygen sensors at different locations in a bird's respiratory system. Give the bird one breath of pure OI, followed by a breath of normal air. Record when oxygen reaches different sensors. The breath marked by pure O, as inhaled. Results ion, Lirac, T to the posterior air sacs. Euro during the next inhalation, the marked breath flows from the lungs to the anterior air sacs. Exhalation. Breath 2. Finally, during the next exhalation, the L breath marked by pure O is expelled. Conclusion. Air travels through the lungs in one direction, from the posterior to the anterior air sacs. 2 cycles of inhalation and exhalation are required for the air to travel through the bird's respiratory tract. Fig. Point 7. The path of airflow through bird lungs. The era. Bird takes in with one breath. Blue travels through the lungs in one direction, from the posterior to the anterior air sacs. The gas exchange surfaces. They are so numerous that they provide an enormous surface area for gas exchange. The puzzle of how birds breathe was solved by an experiment that placed small oxygen sensors at different locations in the air sacs and airways of birds. The bird could then be exposed to pure oxygen for just a single breath, and the progress of that single breath through the bird's gas exchange system could be followed by the oxygen sensors. This experiment showed that a single breath remains in the bird's gas exchange system for 2 cycles of inhalation and exhalation, and that the air sacs work as bellows, maintaining a continuous and unidirectional flow of fresh air through the lungs. See Figure 7. The advantages of the bird gas exchange system are similar to those of fish gills. The air sacs keep fresh air flowing unidirectionally and continuously over the gas exchange surfaces. Thus, the bird can supply its gas exchange surfaces with a continuous flow of fresh air that has a pO close to that of the ambient air, even when the pO of the ambient air is only slightly above the pO of the blood. O can diffuse from air to blood. Tidal breathing in humans. Lungs evolved in the first, air gulping, vertebrates as outpocketings of the digestive tract. Although their structure has evolved considerably, lungs remain dead end sacs in all air-breathing vertebrates except birds. Because lungs are dead end sacs, ventilation cannot be constant and unidirectional, but must be tidal. Air flows in and exhaled gases flow out by the same route. A spirometer is an old-fashioned device that has been replaced by electronic flow meters, but we can use a virtual spirometer to visualize how we use our lung capacity in breathing. Figure 8. When we are at rest, the amount of air that moves in and out per breath is called the tidal volume, about 500 milliliters for an average human adult. We can breathe much more deeply and inhale more air than our resting tidal volume. The additional volume of air we can take in above normal tidal volume is our inspiratory reserve volume. Conversely, we can forcefully exhale more air than we normally do during a resting exhalation. This additional amount of air is the expiratory reserve volume. The combined tidal volume, inspiratory reserve volume, and expiratory reserve volume is the vital capacity. The vital capacity of an athlete once generally greater than that of a non-athlete, and vital capacity decreases with age. Vital capacity is not the entire lung volume. Even after the most extreme exhalation possible, some air remains in the lungs. The lungs and airways cannot be collapsed completely. They always contain a residual volume. The total lung capacity is the sum of the residual volume and the vital capacity. Tidal breathing severely limits the partial pressure gradient available to drive the diffusion of O from air into the blood. Fresh air is not moving into the lungs during part of the breathing cycle. Therefore, the average pO of air in the lungs is considerably less than it is in the air outside the lungs. Furthermore, the incoming fresh air mixes with the stale air that was not expelled by the previous exhalation. The volume of this stale air is the sum of the residual volume and, depending on how deeply one is breathing, some or all of the expiratory reserve volume. 28 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Research method. Breathing into a spirometer inspiratory reserve. Q. Kernaval. N. RT Matrapi GDP. Y. Characteristics AF Rusar air OL air and adding capacity direction of breathing to become monster changes O of the lungs to I maximum chart movement. S. I13 Bolua. Aleph 2 deep equals. The scale in Figure 8 shows a typical resting breathing pattern in which a tidal volume of 500 milliliters of fresh air mixes with over 2,000 milliliters of stale air before reaching the gas exchange surfaces in our lungs. In this situation, even though the pO in the ambient air is 150 milliliters Hg, the pO of the air that reaches the gas exchange surfaces is only about 100 milliliters Hg. About 150 milliliters of the residual volume exists in airways, where gas exchange cannot occur. This volume is called the anatomical dead space. Because the anatomical dead space has to be filled with a portion of each incoming breath, shallow breathing can greatly reduce the amount of O that is available at the gas exchange surfaces. For this reason, patients recovering from surgery are encouraged to breathe deeply even though it hurts. Some lung diseases, such as emphysema, increase the anatomical dead space of the lungs and make this problem worse. In addition to reducing the pO gradient, tidal breathing eliminates the possibility of a significant adaptation we noted in fish gills, countercurrent gas exchange. Because air enters and leaves the gas exchange structures by the same route, there is no anatomical way that blood could flow countercurrent to the airflow. To offset these inefficiencies of tidal breathing, mammalian lungs have some design features that maximize the rate of gas exchange, an enormous surface area and a very short path length for diffusion. Mammalian lungs serve the respiratory needs of mammals well. We will use as our example the respiratory system of humans. Gas exchange in human lungs. Air enters the lungs through the oral cavity or nasal passage, which join together in the pharynx. Figure 9a. Below the pharynx, the esophagus conducts food to the stomach, and a single trachea leads to the lungs. At the beginning of this airway is the larynx, or voice box, which houses the vocal cords. The larynx is the Adam's apple that you can see or feel on the front of your neck. The trachea is about 2 centimeters in diameter. Its thin walls are prevented from collapsing by C-shaped bands of cartilage that support them as air pressure changes during the breathing cycle. If you run your fingers down the front of your neck just below your larynx, you can feel a couple of these bands of cartilage. The trachea branches into 2 smaller bronchi, one leading to each lung. The bronchi branch repeatedly to generate a tree-like structure of progressively smaller airways extending to all regions of the lungs. After 4 branchings, the cartilage supports disappear, marking the transition to bronchioles. After about 16 branchings, the bronchioles are smaller than the diameter of a pencil lead, and tiny, thin-walled air sacs called alveoli begin to appear. After about 6 more branchings, the airways end in clusters of alveoli. Figure 9b. Because the airways only conduct air to and from the alveoli and do not themselves conduct gas exchange, their volume is anatomical dead space. The alveoli are the sites of gas exchange. The total number of alveoli in human lungs is about 300 million. Even though each alveolus is very small, their combined surface area for diffusion of respiratory gases is about 70 meters greater than, about 1/4 the size of a basketball court. Each alveolus is made of very thin cells. Between and surrounding the alveoli are networks of Each alveolus is made of very thin cells. Between and surrounding the alveoli are networks of capillaries, whose walls are also made up of exceedingly thin cells. Where capillary meets alveolus, very little tissue separates them. Figure 9c, so the length of the diffusion path between air and blood is less than 2 pm. Respiratory tract secretions aid ventilation. Mammalian lungs have 2 other important adaptations that do not directly influence their gas exchange properties, but to affect the process of ventilation, the production of mucus and the production of surfactant. Many cells lining the airways produce a sticky mucus that captures bits of dirt and microorganisms that are inhaled. Other cells lining the airways have cilia whose beating continually sweeps the mucus, with its trapped debris, up toward the pharynx, where it can be swallowed or spit out. This phenomenon, called the mucus escalator, can be adversely affected by inhaled pollutants. Smoking one cigarette can immobilize the cilia of the airways for hours. A smoker's cough results from the need to clear the obstructing mucus from the Institute for Advanced Studies, Jodhpur 29. Unit 7 System Physiology Animal. Airways. When the mucus escalator is out of order, the genetic disease cystic fibrosis causes respiratory problems by affecting the respiratory mucus. Due to a faulty chloride channel, the mucus that is produced is dehydrated, thick, and sticky. This mucus is difficult to clear. Sedabrium bacteria remain in the airways, resulting in blockage and infections. A surfactant is a chemical substance that reduces the surface tension of a liquid by interfering with the cohesive forces that create it. Surface tension gives the surface of a liquid the properties of an elastic membrane. The thin film of fluid covering the air-facing surfaces of the alveoli has surface tension, which contributes to the elasticity of the lungs. This elasticity must be overcome to inflate the lungs. Phi. Dick and eggs lives within the thoracic cavity, which I bounded by the ribs. R the diaphragm. Y. Hash ural cavit. FARBRXJ, I, tilde LARIRX. NLLLF, underscore X, dup R, M. LA and towards the lungs from the O tilde Misal passage. The thoracic cavity ANC. Flissural Ursan Briarios LNG also po T versus He RNGS. Surface tension normally is reduced by certain cells in the alveoli, which are stimulated to produce surfactant molecules when they are stretched. If a baby is born more than a month prematurely, however, these cells may not yet be producing surfactant. If a baby is born more than a month prematurely, however, these cells may not yet be producing surfactant. Such a premature baby has great difficulty breathing because an enormous effort is required to stretch the alveoli. A baby with this condition, known as respiratory distress syndrome, may die from exhaustion and suffocation. Common treatments have been to put the baby on a respirator to assist its breathing and to give it hormones to speed its lung development. A new approach, however, is to apply surfactant to the lungs via an aerosol. The branchier de major AR. Passageries of the Ings, they. For CDW0 the L-Ronchiodes, which. Era Finsley branched. Opening parenthesis closing square bracket. L-almethylmn and S and L-phys and GFL and E. Via the trachea and branchie. Plus OF. R cryoginated equals, alveolus. Elud B hort. Cryptonated thogenated. Lacey to heart layout from higher red blood call. Intheracar of, TI alveolus. Lungs are ventilated by pressure changes in the thoracic cavity. As figure 9a shows, human lungs are suspended in a right and a left thoracic cavity. Each thoracic cavity is a closed compartment bounded on the top by the shoulder girdle, on the side by the rib cage, at opening square bracket. Alveoli. Section the human respiratory system. The diagrams trace the hierarchy of human respiratory structures, from the lungs to the minuscule iode. The midline by tissue surrounding the heart and digestive tract, and on the bottom by a dome sheet of muscle, the diaphragm. Each thoracic cavity is lined by a continuous sheet of pleural membrane, which doubles back on itself to cover the lungs. Because the plural. 30 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Membranes also constitute closed compartments within the thoracic cavity. They are called pleural cavities. Within the pleural cavity is a thin film of fluid that lubricates the inner surfaces of the pleural membrane so they can slip and slide against each other during breathing movements, but surface tension makes it difficult to pull the pleural membranes apart. Think of two wet panes of glass, or two wet microscope slides. You can easily slide them past each other, but it is difficult to separate them. In addition to being stuck to each other by surface tension, the pleural membranes are attached to the wall of the thoracic cavity and to the surface of the lung. Breathing involves changes in the volume of the thoracic cavity. Because the pleural membranes are attached to the walls of the thoracic cavity, and because the pleural cavity is a closed compartment, any increase in the thoracic cavity volume creates a subatmospheric pressure, which we will refer to as a negative pressure inside the pleural cavity. Even between breaths, there is normally a slight negative pressure in the pleural cavity because the rib cage is pulling outward and the elasticity of the lung tissue is pulling inward. This slight suction keeps the alveoli partly inflated. If the thoracic cavity is punctured by a knife wound, for example, air leaks into the pleural cavity, and the pressure from this air causes the lung to collapse. If the wound is not sealed, breathing movements pull air into the pleural cavity rather than into the lung, and ventilation of the alveoli in that lung ceases. Inhalation is initiated by contraction of the muscular diaphragm. As the diaphragm contracts, it expands the thoracic cavity, pulls on the pleural membranes, and increases the negative pressure in the pleural cavity. The closed pleural cavity cannot expand, so it pulls on the lungs. Because the lungs are not a closed cavity, but have an airway to the atmosphere, they can expand in volume, and air rushes in through the trachea from the outside. Exhalation begins when the contraction of the diaphragm ceases. The diaphragm relaxes and moves up, and the elastic recoil of the lung tissues pushes air out through the airways. When a person is at rest, inhalation is an active process and exhalation is a passive process. Figure 10. The diaphragm is not the only muscle that can change the volume of the thoracic cavity. Between the ribs are two sets of intercostal muscles. The external intercostal muscles expand the thoracic cavity by lifting the ribs up and outward. The internal intercostal muscles decrease the volume of the thoracic cavity by pulling the ribs down and inward. When heavy demands are placed on the gas exchange system, such as during strenuous exercise, the external intercostal muscles increase the volume of air inhaled, making use of the inspiratory reserve volume, and the internal intercostal muscles increase the amount of air exhaled, making use of the expiratory reserve volume. The abdominal muscles can also aid in breathing. When they contract, they cause the abdominal contents to push up on the diaphragm and contribute to the expiratory reserve volume. Remember that ventilation and perfusion work together to maximize the partial pressure gradients across the gas exchange surface. Ventilation delivers O to the environmental side of the exchange surface, where it diffuses into the body and is swept away by perfusion. The reverse is true for the exchange of CO. Perfusion delivers it to the exchange surface, where it diffuses out and is swept away by ventilation. Inhalation, exhalation. Alveolar pressure, pleural cavity pressure. PRES SU RE. Plus diaphragm contracts. During inhalation. Plus diaphragm contracts. Plus thoracic cavity expands. Thoracic cavity contracts plus intrapleural pressure becomes intrapleural pressure becomes more negative, less negative. Lungs expand, lungs contract. Air rushes in, gases in lungs are expelled. During exhalation, diaphragm relaxes. Fig 10 into the lungs and out again. Inhalation is an active process spurred by the contraction of the diaphragm. Exhalation generally is a passive process as the diaphragm relaxes. Blood transport of respiratory gases. Perfusion of the lungs is one of the functions of the circulatory system. The circulatory system uses a pump, the heart, and a network of vessels to transport extracellular fluids and associated cells, blood, around the body. Here we will discuss only one aspect of perfusion, how the respiratory gases are transported in the blood. The liquid part of the blood plasma, carries some O in solution, but its ability to transport O is quite limited. The blood plasma of a human, for example, can contain in solution only about 0.3 milliliters of O per 100 milliliters of plasma, which is inadequate to support even basal metabolism. To increase its O transport capacity, the blood of most animals, vertebrate and invertebrate, also contains molecules that can bind reversibly to O, depending on its partial pressure. These molecules pick up or bind O where its partial pressure is high and release it where its partial pressure is lower. There are many O transport molecules in the animal kingdom, but in vertebrates this role is played by hemoglobin contained in red blood cells. Hemoglobin increases the capacity of blood to transport O by about 60-fold. Hemoglobin combines reversibly with oxygen. Red blood cells contain enormous numbers of hemoglobin molecules. Hemoglobin 1 is a protein consisting of 4 polypeptide subunits. Each of these. Institute for Advanced Studies, Jodhpur 31. Unit 7 System Physiology Animal. Polypeptide surrounds a heme group, an iron-containing ring structure that can reversibly bind a molecule of O. Thus, each molecule of hemoglobin can bind to 4 molecules of O. As O diffuses into the red blood cells, it binds to hemoglobin. Once O is bound, it cannot diffuse back across the red cell plasma membrane. By binding O molecules as they enter the red blood cells, hemoglobin maximizes the partial pressure gradient driving the diffusion of O into the cells. In addition, it enables the red blood cells to carry a large amount of O to the tissues of the body. The ability of hemoglobin to pick up or release O depends on the PO of its environment. When the PO of the blood plasma is high, as it usually is in the lung capillaries, each molecule of hemoglobin can carry its maximum load of 4 molecules of O. As the blood circulates through the rest of the body, it encounters lower PO values. At these lower PO values, the hemoglobin releases some of the O it is carrying. Figure 11. The relation between PO and the amount of O bound to hemoglobin is not linear, but S-shaped sigmoidal. The sigmoidal hemoglobin O binding curve in figure 11 reflects interactions between the 4 subunits of the hemoglobin molecule. At low PO values, only one subunit will bind an O molecule. When it is so, the shape of that subunit changes, causing an alteration in the quaternary structure of the whole hemoglobin molecule. That structural change makes it easier for the other subunits to bind a molecule of O, that is, their O D affinity is increased. Therefore, a smaller increase in PO is necessary to get most of the hemoglobin molecules to bind to O molecules, that is, to become 50% saturated, then was necessary to get them to bind one O molecule to become 25% saturated. This influence of the binding of O by one subunit on the O affinity of the other subunits once called positive cooperativity. The average PY of the oxygenated blood returning to the heart is 40 milliliters Hg. The PY of blood leaving the lungs is about 100 milliliters Hg. 25% of the O in arterial blood is released to tissues during rest or light exercise. An oxygen reserve of hemoglobin can be released to tissues. Molecule will find a place to bind. Therefore, it takes a relatively greater PO to achieve 100% saturation. This is a good place to mention the danger posed by carbon monoxide (CO), which can come from a faulty furnace or from burning a fuel such as charcoal or kerosene without adequate ventilation. CO binds to hemoglobin with a higher affinity, 240 times higher than O. Thus, county prevents hemoglobin from transporting and releasing O to the tissues of the body. The victim loses consciousness and can die because the brain lacks O. The O binding properties of hemoglobin help get O to the tissues that need it most. In the lungs, where the PO is about 100 milliliters Hg, hemoglobin is 100% saturated. The PO in blood returning to the heart from the body is usually about 40 milliliters Hg. You can see from figure 11 that at this PO, the hemoglobin is still about 75% saturated. This means that as the blood circulates around the body, only about 1 in 4 of the 0 molecules it carries is released to the tissues. This system seems inefficient, but it is really quite adaptive because the hemoglobin keeps 75% of its O in reserve to meet peak demands. When a tissue becomes starved of O and its local PO falls below 40 milliliters Hg, the hemoglobin flowing through that tissue is on the steep portion of its sigmoid binding curve. That means that relatively small decreases in PO below 40 milliliters Hg will result in the release of lots of O to the tissue. Thus, the positive cooperativity of O binding by hemoglobin is very effective in making O available to the tissues precisely when and where it is needed most. Myoglobin holds an O reserve. Muscle cells have their own oxygen binding molecule, myoglobin. Myoglobin consists of just one polypeptide chain associated with an iron-containing ring structure that can bind one molecule of O. Myoglobin has a higher affinity for O than hemoglobin does, so it picks up and holds O at PO values at which hemoglobin is releasing its bound O. Figure 12. Myoglobin 100 equals 80 equals llama hemoglobin human fetal hemoglobin 60 human maternal hemoglobin 40 OXYGEN. Figure 11. The binding of O to hemoglobin depends on pG. Hemoglobin in blood leaving the lungs is 100% saturated. 4 molecules of O are 20 bound to each hemoglobin molecule. Most hemoglobin molecules will drop only one of their 4 O molecules as they circulate through the body and are still 75% saturated when the blood returns to the lungs. The steep portion 11 ILL of this oxygen binding curve comes into play when tissue PO falls below the 2040 and O 80 100 normal 40 milliliters Hg, at which point the hemoglobin will unload its O reserves. pp and Hg once the third molecule of O is bound, the relationship seems to change as a larger increase in PO is required for the hemoglobin to reach 100% saturation. This upper band of the sigmoid curve is due to a probability phenomenon. The closer we get to having all subunits occupied, the less likely it is that any particular O. Figure 12 oxygen binding adaptations. The different hemoglobins and myoglobin have different oxygen binding properties adapted to different circumstances. The hemoglobin of llamas, for example, is adapted for binding O at high altitudes where PO is low. 32 Institute for Advanced Studies, Jodhpur. The physiology animal. Myoglobin provides a reserve of O for the muscle cells for times when metabolic demands are high and blood flow is interrupted. Interruption of blood flow in muscles is common because contracting muscles constrict blood vessels. When tissue PO values are low and hemoglobin can no longer supply more O, myoglobin releases its bound O. Diving mammals such as seals have high concentrations of myoglobin in their muscles, which is one reason they can stay underwater for so long. Even in non-living animals, muscles called on for extended periods of work frequently have more myoglobin than muscles that are used for short, intermittent periods. The affinity of hemoglobin for O is variable. Various factors influence the O binding properties of hemoglobin, thereby influencing O delivery to tissues. In this section we examine 3 of those factors: the chemical composition of the hemoglobin, pH, and the presence of 2,3-bisphospholic acid (BPG). Hemoglobin composition. There is more than one type of hemoglobin because the chemical composition of the polypeptide chains that form the hemoglobin molecule varies. The normal hemoglobin of adult humans has each of 2 kinds of polypeptide chains, 2 A globin chains and 2 F globin chains, and the oxygen binding characteristics shown in figure 11. Before birth, the human fetus has a different form of hemoglobin consisting of 2 A globin and 2 Y globin chains. The functional difference between these 2 types of hemoglobin is that the fetal hemoglobin has a higher affinity for O. Therefore, the hemoglobin O binding curve of fetal hemoglobin is shifted to the left in comparison to the curve for adult hemoglobin. See figure 12. You can see from these curves that if both types of hemoglobin are at the same PO, the fetal hemoglobin will pick up O released by its mother's adult hemoglobin. This difference in O affinities facilitates the transfer of O from the mother's blood to the blood of the fetus in the placenta. Llamas and biquies are native to the Andes Mountains of South America. In the natural habitat of these mammals, more than 5,000 meters above sea level, the PO is below 85 Hg, and the PO in their lungs is about 50 milliliters Hg. Thus, the hemoglobins of these animals must pick up O in an environment that has a low PO. The hemoglobins of llamas and biquies have oxygen binding curves to the left of the curves of hemoglobins of most other mammals. In other words, their hemoglobin can become saturated with O at lower PO values than those of other mammals. pH. The oxygen binding properties of hemoglobin are also influenced by physiological conditions. The influence of pH on the function of hemoglobin is known as the Bohr effect. As blood passes through metabolically active tissue such as exercising muscle, it picks up acidic metabolites such as lactic acid, fatty acids, and CO, and blood pH falls. The excess H ions bind preferentially to deoxygenated hemoglobin and decrease the affinity of that hemoglobin for O. As a result, the oxygen binding curve of hemoglobin shifts to the right. This shift means that the hemoglobin will release more O in tissues where pH is low, another way that O is supplied where and when it is most needed. 2. 3-bisphospholic acid, BPG is a metabolite of glycolysis. Mammalian red blood cells have a high concentration of BPG, which serves as an important regulator of hemoglobin function. BPG, like XSH, ions, reversibly combines with deoxygenated hemoglobin and lowers its affinity for O. The result is that at NEPO, hemoglobin releases more of its bound O than it otherwise would. In other words, BPG shifts the oxygen binding curve of mammalian hemoglobin to the right. When humans go to high altitudes, or when they cease being sedentary and begin to exercise, the level of BPG in the red blood cells goes up and makes it easier for the hemoglobin to deliver more O. When humans go to high altitudes, or when they cease being sedentary and begin to exercise, when humans go to high altitudes, or when they cease being sedentary and begin to exercise, the level of BPG in the red blood cells goes up and makes it easier for the hemoglobin to deliver more O to the tissues. The reason that fetal hemoglobin has a left-shifted hemoglobin O binding curve is that the Y globin chains of fetal hemoglobin have a lower affinity for BPG than do the B globin chains of adult hemoglobin. CO is transported as bicarbonate ions in the blood. Delivering O to the tissues is only half of the respiratory function of the blood. The blood also must take carbon dioxide, a metabolic waste product, away from the tissues. Figure 13. CO is highly soluble and readily diffuses through cell membranes, moving from its site of production in the tissues into the blood, where the partial pressure of carbon dioxide (PCO) I1 is lower. However, very little dissolved Colorado is transported by the blood. Most Colorado produced by the tissues is transported to the lungs in the form of bicarbonate ions (HCO). Trademark. CO is converted to HCOJ, trademark, transported to the lungs, and then converted back to Colorado in several steps. When Colorado dissolves in water, some of it slowly reacts with the water molecules to form carbonic acid H, CO3, some of which then dissociates into a proton H, and a bicarbonate ion HCO. This reversible reaction is expressed as follows. CO plus H, O equals H, CO equals H plus HCO. In the blood plasma, the reaction between Colorado and H0 proceeds slowly. But it is a different story in the endothelial cells of the capillaries and in the red blood cells, where the enzyme carbonic anhydrase speeds up the conversion of CO to HCO. The newly formed carbonic acid dissociates, and the resulting bicarbonate ions enter the plasma in exchange for C. See figure 13. By converting Colorado to H, cos, carbonic anhydrase reduces the PRP in these cells and in the plasma, facilitating the diffusion of CO from tissue cells to endothelial cells, plasma, and red blood cells. Some Colorado is also carried in chemical combination with hemoglobin. In the lungs, the reactions involving Colorado and bicarbonate ions are reversed. Remember that an enzyme such as carbonic anhydrase only speeds up a reversible reaction. It does not determine its direction. The direction is determined by concentrations of reactants and products. Ventilation keeps the CO concentration in the alveoli low, so Colorado diffuses from the blood plasma into the alveoli, lowering the CO concentration in the blood, which favors the conversion of HCO into Colorado. Institute for Advanced Studies, Jodhpur 33. Unit 7 System Physiology Animal. BL or body TS SUS, Epsom BL red blood cells. We must breathe every minute of our lives, but we don't usually worry about our need to breathe, or even think about it very often. Breathing is an autonomic function of the nervous system. The breathing pattern easily adjusts itself around other activities, such as speech and eating, and breathing rates change to match the metabolic demands of our bodies. In this section we examine how the regular breathing cycle is generated and controlled. Breathing is controlled in the brainstem. The autonomic nervous system maintains breathing and modifies its depth and frequency to meet the demands of the body for O, supply in Colorado, elimination. Breathing ceases if the spinal cord is severed in the neck region, showing that the breathing pattern is generated in the brain. If the brainstem is cut just above the medulla, the segment of the brainstem just above the spinal cord, and a regular breathing pattern remains. Figure 14. Tip Fig. 1-4 breathing is generated in the brainstem. Basic breathing rhythm is generated in the medulla and is modified by neurons in or above the pons. Normal breathing. If the brainstem is cut below the pons but above the medulla, AN breathing continues but is irregular. If the spinal cord in _L equals the neck is severed, L breathing ceases. Groups of neurons within the medulla increase their firing rates just before an inhalation begins. As more and more of these neurons fire, and fire faster and faster, the diaphragm contracts. Suddenly the neurons stop firing, the diaphragm relaxes, and exhalation begins. Exhalation is usually a passive process that depends on the elastic recoil of the lung tissues. When breathing demand runs high, however, as during strenuous exercise, motor neurons for the intercostal muscles are recruited, which increases both the inhalation and the exhalation volumes. Brain areas above the medulla modify breathing to accommodate speech, ingestion of food, coughing, and emotional states. Regulating breathing requires feedback information. When breathing changes or when metabolism changes, it alters the PG and the PCP in the blood. We should therefore expect the blood levels of one or both of these gases to provide feedback information to the breathing rhythm generator in the medulla. Experiments in which subjects breathe air with different PY and PCO concentrations lead us to conclude that humans and other mammals are remarkably insensitive to falling blood levels of O, but very sensitive to increases in the PCO of the blood. Figure 15. Percent CO in inhaled air. 1 2 3 4 5 6 7 8 9 1. Figure 15. Carbon dioxide effects. Breathing rate. Breathing is more sensitive to increased carbon dioxide content in inhaled air than to its decreased oxygen content. We may ask whether it is a rise in the PCO of the blood that stimulates increased breathing when we exercise. To answer this question, researchers ran dogs on treadmills at different speeds. As the speed of the treadmill increased, the respiratory gas exchange rate of the dogs increased, but the PCO of the dog's blood remained constant. Before concluding that blood PCP is not the metabolic feedback information for breathing rate, however, the researchers changed their experiment. 34 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Instead of increasing the speed of the treadmill, they gradually increased its slope so that the dogs were running at the same speed, but were working harder because they were running uphill. In this experiment, the PCO of the blood increased as the slope of the treadmill increased, and as the respiratory gas exchange rate increased. The researchers concluded that the PCQ of the blood is the primary metabolic feedback information for breathing. However, when an animal starts to run or changes its running speed, additional feedback information from receptors in muscles and joints changes the sensitivity of the CO sensors. An example of feed-forward information. Where are partial pressures of gases in the blood sensed? The major site of CO sensitivity is an area on the ventral surface of the medulla, not far from the groups of neurons that generate the breathing rhythm. Primary sensitivity to PG in the blood resides in nodes of tissue on the large blood vessels leaving the heart, the aorta and the carotid arteries. Figure 16. These carotid and aortic bodies receive enormous supplies of blood relative to their small size, and they contain chemoreceptors. If the blood supply to these structures decreases, or if the pG of the blood falls dramatically, the chemoreceptors are activated and send nerve impulses to the breathing control center. Although we are not very sensitive to changes in blood pG, the carotid and aortic bodies can stimulate increases in breathing during exposure to very high altitudes or when blood volume or blood pressure is very low. Neural input from higher neurons at brain centers, MG excite breathing. Neurons in medulla chemoreceptors on the surface of the medulla are sensitive to the partial pressure of carbon dioxide and the pH of the cerebral spinal fluid. Chemoreceptors on large blood vessels leaving the heart are sensitive to the medulla. Oxygen in the blood. B breathing. Control area equals spinal cord. Carotid body 18. Carotid artery G4. Aorta. Aortic bod Y underscore G output top respiratory muscles. Heart. Figure 16 feedback information controls breathing. The body uses feedback information from chemosensors in the heart and the brain to match breathing rate to metabolic demand. Institute for Advanced Studies, Jodhpur 35. Unit System Physiology Animal. D nervous system, neurons, action potential, gross neuroanatomy of the brain and spinal cord, central and peripheral nervous system, neural control of muscle tone and posture. Nervous systems, cells and functions. Nerve cells, or neurons, are specialized to receive information, encode it, and transmit it to other cells. Neurons and their specialized supportive cells, called glial cells, make up nervous systems. Animals receive various kinds of information from both inside and outside their bodies. This information is received and converted, or transduced, by sensory cells, also called receptor cells, into This information is received and converted, or transduced, by sensory cells, also called receptor cells, into electric signals that can be transmitted and processed by neurons. To cause behavioral or physiological responses, a nervous system communicates these signals to effectors, such as muscles and glands. Nervous systems process information. Simple animals such as sea anemones can process information with simple networks of neurons that do little more than provide direct lines of communication from sensory cells to effectors. Figure. The anemone's nerve net is most developed around the tentacles in the oral opening, where it facilitates detection of food or danger and causes tentacles to extend or retract. Bilaterally symmetrical animals, such as earthworms, that move more rapidly through their environments need to process and integrate larger amounts of information. This need is met by clusters of neurons called ganglia. Figure 1b. Ganglia serving different functions may be distributed around the body, as in the earthworm or the squid. Figure 1c. Frequently, one pair of ganglia is larger and more central than the others and is therefore given the designation of brain. Invertebrates, most of the cells of the nervous system are found in the brain and the spinal cord, the sites of most information processing, storage, and retrieval. Figure 1d. Therefore, the brain and spinal cord are called the central nervous system (CNS). Information is transmitted from sensory cells to the CNS and from the CNS to effectors via neurons that extend or reside outside of the brain and the spinal cord. These neurons and their supporting cells are called the peripheral nervous system. Vertebrates differ greatly in their behavioral complexity and in their physiological specializations. Even the smaller and simpler nervous systems of invertebrates can be more complex. Consider the nervous systems of small spiders that have programmed within them the thousands of precise movements necessary to construct a beautiful web without prior experience. Neurons are the functional units of nervous systems. Although nervous systems vary enormously in structure and function, neurons function similarly in animals as different as squids and humans. Their plasma membranes generate electric signals, called nerve impulses or action potentials, and conduct these signals from one location on a neuron to the most distant reaches of that cell, a distance that can be more than a meter in a human and many meters in a whale. Most neurons have 4 regions: a cell body, dendrites, an axon, and axon. Terminals. Figure 2a, but the variation among different types of neurons is considerable. Figure 2b. The cell body contains the nucleus and most of the cell's organelles. Many projections may sprout from the cell body. Most of these projections are bush-like dendrites, from the Greek dendron, tree, which bring information from other neurons or sensory cells to the cell body. The degree of branching of the dendrites differs among different types of neurons. In most neurons, one projection is much longer than the others, and is called the axon. Axons usually carry information away from the cell body. The length of the axon also differs among different types of neurons. Some axons are remarkably long, such as those that run from the spinal cord to the toes. B. Brain. Same mental tilde and 7. In the earthworm, ganglia in each segment coordinate movement and an anterior brain controls nerve complex behavior. The human brain and spinal cord are the central nervous system. In squid, more complex behaviors are served by collections of neurons in specialized ganglia. One nervous systems vary in size and complexity as we compare animals that have increasingly complex sensory and behavioral abilities. We find that information processing is increasingly central. Is in ganglia collections of neurons or in a brain. 36 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Generalized neuron anatomy. Dendrites receive information from other neurons. The cell body contains the nucleus and most cell organelles. Base of axon, axon. Hillock integrates information collected by dendrites and initiates nerve impulses. The axon conducts nerve impulses away from the cell body. 2 neurons. A generalized diagram. Open neuron. B neurons from different parts of the mammalian nervous system are specifically adapted to their functions. B specialized neurons. Neurons with bushy dendrites collect neurons with fewer dendrites information from many other cells. Process fewer inputs. 3i underscore retina. B versus cerebellum percent. Axons are the telephone lines of the nervous system. Information received by the dendrites can cause the cell body to generate a nerve impulse, which is then conducted along the axon to the cell that is its target. At the target cell, which can be another neuron, a muscle cell, or an endocrine cell, the axon divides into a spray of fine nerve endings. At the tip of each of these tiny nerve endings is a swelling, called an axon terminal, that comes very close to the target cell. Where an axon terminal comes close to another cell, the membranes of both cells are modified to form a synapse. In most cases, a space only about 25 nanometers wide separates the two membranes. A nerve impulse arriving at an axon terminal causes an increase of chemical messenger molecules called neurotransmitters stored in the axon terminal to be released. The released neurotransmitters diffuse across the space and bind to receptors on the plasma membrane of the target cell. Thousands of synapses impinge on most individual neurons. Integration of information in the nervous system is possible because the neuron can receive information, synaptic inputs, from many sources before producing nerve impulses that travel down its single axon to target cells. Glial cells are also important components of nervous systems. Neurons are not the only type of cell in the nervous system. In fact, there are more glial cells than neurons in the human brain. Like neurons, glial cells come in several forms and have a diversity of functions. Some glial cells physically support and orient the neurons and help them make the right contacts during embryonic development. Other glial cells insulate axons. In the peripheral nervous system, Schwann cells wrap around the axons of neurons, covering them with concentric layers of insulating plasma membrane. Figure 3. Other glial cells called oligodendrocytes perform a similar function in the central nervous system. Myelin is the covering. Myelin is the covering produced by Schwann cells and oligodendrocytes, and it gives many parts of the nervous system a glistening white appearance. A myelin-producing Schwann cell. Site and direction of myelin growth in multiple layers of plasma membrane. Myelin insulate the axon. 3 wrapping up an axon. Schwann cells wrap axons in the peripheral nervous system with layers of myelin, a type of plasma membrane that provides electrical insulation. B. A myelinated axon. Seen in cross-section through an electron microscope. Glial cells are well known for the many supportive roles they play. Some supply neurons with nutrients, others consume foreign particles and cell debris. Glial cells also help maintain the proper ionic environment around neurons. Although they have no axons and do not generate or conduct nerve impulses, some glial cells communicate with one another electrically through gap J junctions, a special type of connection that enables ions to flow between cells. Glial cells called astrocytes because they look like stars contribute to the blood-brain barrier, which Institute for Advanced Studies, Job 37. Unit 7 System Physiology Animal. Protects the brain from toxic chemicals in the blood. Blood vessels throughout the body are very permeable to many chemicals, including toxic ones, which would reach the brain if this special barrier did not exist. Astrocytes help form the blood-brain barrier by surrounding the smallest, most permeable blood vessels in the brain. The barrier is not perfect, however. Since it consists of plasma membranes, it is permeable to fat-soluble substances such as anesthetics and alcohol. Neurons function in networks. As we learn more about the properties of neurons, it is important to keep in mind that nervous systems depend on neurons working together. The simplest neuronal network consists of 3 cells, a sensory neuron connected to a motor neuron connected to a muscle cell. Most of the neuronal networks that carry out the functions of the human nervous system are much more complex and consist of many more neurons. The human brain contains an estimated 10 inches neurons, and most of those neurons receive information from 1,000 or more synapses. Thus, there may be as many as 10 inches synapses in the human brain. Therein lies the incredible ability of the human brain to process information. This astronomical number of neurons and synapses is divided into thousands of distinct but interacting networks that function in parallel. But before we can understand how even one of these networks works, we must understand the properties of individual neurons that allow them to generate and conduct nerve impulses. Neurons, generating and conducting nerve impulses. The insides of cells are electrically negative in comparison to the outsides. The difference in electric potential, or voltage, across the plasma membrane of a cell is called its membrane potential. In an unstimulated neuron, this voltage difference is called a resting potential. Membrane potentials can be measured with electrodes. An electrode can be made from a glass pipette pulled to a very sharp tip and filled with a solution containing ions that conduct electric charges. Using such electrodes, we can record very tiny local electrical events. If a pair of electrodes is placed one on each side of the plasma membrane of a resting axon, they measure a voltage difference of about 60 millivolts MV. Figure 4. Research method. Neuron. EY. Equals in Y battery. The resting potential provides a means for neurons to respond to a stimulus. A neuron is sensitive to any chemical or physical factor that causes a change in the resting potential across a portion of its plasma membrane. The most extreme change in membrane potential is an action potential, which is a sudden and rapid reversal in the voltage across a portion of the plasma membrane. For 1 or 2 milliseconds, a bioelectric current crosses the membrane and the inside of the cell becomes more positive than the outside. Nerve impulses are action potentials that move along axons. Simple electrical concepts underlie neuronal function. Voltage potential or electric charge difference is a tendency for electrically charged particles such as electrons or ions to move between 2 points. Voltage is to the flow of electrically charged particles what pressure is to the flow of water. If the negative and the positive poles of a battery are connected by a copper wire, electrons flow from negative to positive because there is a voltage difference between them. This flow of electrons is an electric current, and it can be used to do work, just as a current of water can be used to do work such as turning a turbine. Electric current is carried by electrons in wires, but in solutions and across cell membranes, it is carried not by electrons, but by charged ions. The major ions that carry electric charges across the plasma membranes of neurons are sodium, Na, chloride C, potassium K, and calcium Ca. It is also important to remember that ions with opposite charges attract one another, and those with like charges repel one another. With these basics of bioelectricity in mind, we can ask how the resting potential of the neuronal plasma membrane is created. 38 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. And how the flow of ions through membrane channels is turned on and off to generate action potentials. Ion pumps and channels generate resting and action potentials. The plasma membranes of neurons, like those of all other cells, are lipid bilayers that are impermeable to ions. However, these impermeable lipid bilayers contain many protein molecules that serve as ion channels and ion pumps. Ion pumps and channels are responsible for resting and action potentials. Ion pumps use energy to move ions or other molecules against their concentration gradients. A major ion pump in the plasma membranes of neurons and of all other cells is the sodium-potassium pump. The action of this pump expels Na ions from inside the cell, exchanging them for K ions from outside the cell. Figure 5a. The sodium-potassium pump keeps the concentration of K inside the cell greater than that of the extracellular fluid, and the concentration of Na inside the cell less than that of the extracellular fluid. The concentration difference is established by the pump mean that K would diffuse out of the cell and Na would diffuse in if the ions could cross the lipid bilayer. Ion channels are pores formed by proteins in the lipid bilayer. These water-filled pores allow ions to pass through a membrane, but they are generally selective. They allow some types of ions to pass through more easily than others. Figure 5b. Thus, there are potassium channels, sodium channels, chloride channels, and calcium channels, and there are many different kinds of each. Ions move through channels by diffusion and can move in either direction. The direction and magnitude of net movement of ions through a channel depends on the concentration gradient of that ion type across the plasma membrane, as well as the voltage across that membrane. 5 Long pumps and channels of the sodium-potassium pump actively moves K ions to the inside of a neuron and not T ions to the outside. Beat Long channels allow specific ions to diffuse down their concentration gradient. K ions tend to leave neurons when potassium channels are open, and Na ions tend to enter neurons when sodium channels are open. At Na K pump B, Na and K channels. Potassium channels are the most common open channels in the plasma membranes of resting, non-stimulated neurons. As a consequence, resting neurons are more permeable to K than to any other ion. As figure 6 shows, this characteristic explains the resting potential. Because the potassium channels make the plasma membrane permeable to K, and because the sodium-potassium pump keeps the concentration of K inside the cell much higher than that outside the cell, K tends to diffuse out of the cell through the channels. As positively charged K ions diffuse out of the cell, they leave behind unbalanced negative charges, mostly C, ions and protein molecules generating an electric potential across the membrane that tends to pull positively charged K ions back into the cell. The membrane potential at which the tendency of K ions to diffuse out of the cell is balanced by the negative electric potential pulling them back and is called the potassium equilibrium potential. Outside of cell, the tendency of K ions to O degree O diffuse out leaves in excess of at QC negative charges inside the cell, degree tilde J creating the resting potential. 6 Open potassium channels create the resting potential. Open potassium channels allow K ions to diffuse out of the cell, leaving unbalanced negative charges behind, mostly unclions and protein molecules. The value of the potassium equilibrium potential can be calculated from the concentrations of K on the two sides of the membrane using an equation called the Nernst equation, which is derived from the laws of physical chemistry. Figure 7. In general, the resting potential is a bit less negative than this equation predicts because resting neurons are also slightly permeable to other ions, such as Na and Cl. Ion channels can alter membrane potential. Many ion channels in the plasma membranes of neurons behave as if they contain a gate that opens under some conditions, but closes under other conditions. Voltage-gated channels open or close in response to a change in the voltage across the plasma membrane. Chemically gated channels open or close depending on the presence or absence of a specific molecule that binds to the channel protein, or to a separate receptor that in turn alters the channel protein. Both voltage-gated and chemically gated channels play important roles in neuronal function. Changes in gated channels may perturb the resting potential. Imagine what happens, for example, if sodium channels in the plasma membrane open. Na ions diffuse into the neuron because of their higher concentration on the outside, plus they are attracted to the inside of the cell by its negative charge. As a result of the entry of Na ions, the inside of the cell becomes less negative. When the inside of a neuron becomes less negative or more positive in comparison to its resting condition, its plasma membrane is said to be depolarized. Figure 8a. An opposite change in the resting potential occurs if gated C channels open. The concentration of C ions is normally greater in the extracellular fluid than inside the neuron. This difference is large enough so that the opening of C channels causes Cl to enter the cell even. Institute for Advanced Studies, Jodhpur 39. Unit 7 System Physiology Animal. Research method. IK ions diffuse out of the neuron, the resulting negative potential, creating a negative potential. 7. The Nernst equation. The Nernst equation calculates membrane potential when only one type of ion can cross a membrane that separates solutions with different concentrations of that ion. A resting neuron comes close to that situation because its permeability to K ions is high and its permeability to all other ions is low. Though the membrane potential is negative, the entry of negative charges causes the membrane potential to become even more negative. When the inside of a neuron becomes more negative in comparison to its resting condition, its plasma membrane is said to be hyperpolarized. Figure 8b. The opening and closing of ion channels, which result in changes in the polarity of the plasma membrane, are the basic mechanisms by which neurons respond to electrical, chemical, or other stimuli, such as touch, sound, and light. How does a neuron use a change in its resting membrane potential to process and transmit information? Not channel hash CF channel equals EPY tilde K channel not channel voltage K channel C channel voltage. 8 membranes can be depolarized or hyperpolarized. The resting potential is produced by open K channels. A shift from the resting potential to a less negative membrane potential, as occurs when Na enters the cell through a gated sodium channel, is called depolarization. B hyperpolarization occurs when the membrane potential becomes more negative, as when enters the cell through a gated chloride channel. A change in resting potential may result from input at a synapse. This input, however, is a very local event that affects only a small patch of plasma membrane. How can that information be passed to other parts of the cell? A local perturbation of the resting potential causes a flow of electrically charged ions, which tends to spread the change in membrane potential to adjacent regions of the membrane. This flow of electrically charged ions is an electric current. For example, if positively charged Na plus ions enter the cell through open sodium channels at one location, that positively charged area on the inside of the membrane attracts negative charges from surrounding areas, and thus there is a rapid flow of electric current. However, this local flow of electric current does not spread very far before it diminishes and disappears. The reason why these electric currents do not travel very far is that cell membranes are not completely impermeable to ions. An electric current traveling along the membrane is like water flowing through a leaky hose. The flow of electric current along plasma membranes is useful for transmitting signals over only very short distances. Therefore, axons do not transmit information as a continuous flow of electric current as telephone wires do. However, the local flow of electric current is an important part of the mechanism that generates the signals that axons do transmit over long distances. Action potentials. Sudden changes in ion channels generate action potentials. An action potential is a sudden and major change in membrane potential that lasts for only 1 or 2 milliseconds. Action potentials are conducted along the axon of a neuron at speeds of up to 100 meters per second, which is equivalent to running the length of a football field in a second. If we place the tips of a pair of electrodes on either side of the plasma membrane of a 40 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Resting axon and measure the voltage difference. The reading is about 60 millivolts, as we saw in figure 4. If these electrodes are in place when an action potential travels down the axon, they register a rapid change in membrane potential from 60 millivolts to about plus 50 millivolts. The membrane potential then rapidly returns to its resting level of 60 millivolts as the action potential passes. Figure 9. Voltage-gated sodium channels in the plasma membrane of the axon are responsible for action potentials. At the resting potential, most of these channels are closed. They are called voltage-gated channels because depolarization of the membrane causes them to open. For example, if synaptic input to some part of a neuron is sufficiently strong to cause the plasma membrane of its cell body to neuron. Use oscilloscope screen. Depolarize. That depolarization can spread by local current flow to the base of the axon. See figure 2, where there are voltage-gated sodium channels. When the plasma membrane in this area is depolarized, the channels open briefly, for less than a millisecond. The Na concentration is much higher outside the axon than inside, so when the channels open, Na ions rush into the axon. The entering Na plus makes the inside of the plasma membrane electrically positive. When the membrane is depolarized about 5 to 10 millivolts from the resting potential, a threshold is reached, and a large number of sodium channels open, causing a large, sudden depolarization, and action potential. See figure 9. 9. The course of an action potentials result from rapid changes in voltage-gated sodium and potassium channels. Plus W0T. Tiny K axis. The action. What causes the depolarized axon to return to resting potential? There are 2 contributing factors: the voltage-gated sodium channels close, and voltage-gated potassium channels open. The voltage-gated potassium channels open more slowly than the sodium channels and stay open longer, allowing K to carry excess positive charges out of the axon. As a result, the voltage across the membrane returns to its resting level. Another feature of the voltage-gated sodium channels is that once they open and close, they cannot respond again until after a short delay of 1 to 2 milliseconds. This property can be explained by the assumption that they equals SOL equals dot alt L E ill A0. Same hot channels Macherine activation and activation gates close. The cell reforms. Open, depolarizing gales of pen, causing a gated K Charnel state's resting potential. The cell top wretched, rapid spike of worry, repolarizing a net NSCT ivation gates. Depolarization, an Avian hyperpolarizing a pen. Action potential, _THTN, ZLL. Have 2 voltages inside of gates, an activation gate and an inactivation gate. See figure 9. Under resting conditions, the activation gate is closed and the inactivation gate is open. Depolarization of the membrane to the threshold level causes both gates to change state, but the activation gate responds faster. As a result, the channel is open for a brief time between the opening of the activation gate and the closing of the inactivation gate. The inactivation gate remains closed for 1 to 2 milliseconds before it spontaneously opens again, thus explaining why the membrane has a refractory period before it can fire another action potential. When the inactivation gate finally opens, the activation gate is closed, and the membrane is poised to respond once. Institute for Advanced Studies, Jodhpur 41. Unit 7 System Physiology Animal. Again to a depolarizing stimulus by firing another action potential. Another contribution to the refractory period is the duration of the opening of the voltage-gated potassium channels. Because the potassium channels are open and the sodium channels are closed immediately following an action potential, the membrane potential briefly falls below the normal resting potential. This dip in the membrane potential is called the after hyperpolarization. The difference in the concentration of Na across the plasma membrane and the negative resting potential constitute the battery that drives action potentials. How rapidly does the battery run down? It might seem that a substantial number of non-K ions would have to cross the membrane for the membrane potential to change from 60 millivolts to plus 50 millivolts and back to minus 60 millivolts again. In fact, only a vanishingly small percentage of the Na plus 1 ions concentrated outside the plasma membrane move through the channels during the passage of an action potential. Thus, the effect of a single action potential on the concentration gradients of Na, and K is we can initiate an action potential by using a stimulating electrode to deliver an electric current that depolarizes the membrane enough to reach threshold. Now we can observe the changes in membrane potential associated with the passage of that action potential past the recording electrodes, figure 10b. At the site of the action potential, positive ions flood into the neuron. Once inside, those positive ions spread by current flow to adjacent regions of the axon plasma membrane, making those regions less negative. As this depolarization of the adjacent membrane brings it to threshold, an action potential is generated. Because an action potential always brings the adjacent area of membrane to threshold, the action potential propagates itself along the axon. The action potential normally propagates itself in only one direction, away from the cell body. It cannot reverse itself because the region of membrane it came from is in its refractory period. Action potentials do not travel along all axons at the same speed. They travel faster in larger diameter axons than in small diameter axons. In invertebrates, the axon diameter determines the rate of conduction and axons that transmit messages involved in very small, and it is possible in most cases for the sodium potassium pump to keep the electric stimulus Lewis 33 battery 99 charged even when the neuron is up 4, generating many action potentials every second. An action potential is all or nothing because of the interaction between the voltage-gated sodium channels and the membrane potential. If the membrane once depolarized slightly, some voltage-gated sodium channels open. Some now ions cross the plasma membrane and depolarize it even more, opening more voltage-gated sodium channels, and so on, until the membrane reaches threshold and generates an action potential. This positive feedback mechanism ensures that action potentials always rise to their maximum value. An action potential is self-regenerating because it spreads by local current flow to adjacent regions of the plasma membrane. The resulting depolarization brings those neighboring areas of membrane to threshold. So when an action potential occurs at one location on an axon, it stimulates the adjacent region of axon to generate an action potential, and so on down the length of the axon. Stimulus inverse to NES like E-tri-C stimulus. The axon. Unit 7 System Physiology Animal. Escape behavior are very large. The giant axons that enable squids to escape predators are almost 1 millimeter in diameter. Ion channels and their properties can be studied directly. The size of the squid giant axon made it possible for the British neurophysiologists A. L. Hodgkin and A. F. Huxley to study the electrical properties of axonal membranes almost 70 years ago. They used electrodes to measure voltage differences across the plasma membrane of the squid giant axon and to pass electric current into the axon to change its resting potential. They also changed the concentrations of Na+ and K+ ions both inside and outside the axon and measured the resulting changes in membrane potential. On the basis of their many careful experiments, Hodgkin and Huxley developed the story we have discussed so far. However, they cold only hypothesized the existence of ion channels and their properties, since they were working long before technology enabled the actual demonstration of their existence. Hodgkin and Huxley received the Nobel Prize in 1963. Research method. Recording pipette. A recording pipette filled with a conducting solution is placed in 1, 0 NTAB, T with a neuron's membrane. Mild. Suction J slight suction clamps attach to the _L membrane to the pipette tip. Retracting the pipette removes the retract membrane patch, often with 1 or pipette more ion channels in it. G equals 4 RTHE opening and closing of ion channels can be recorded through FL underscore the pipette. T, oscilloscope tracing of ionic current. Closed. Open. 11 patch clamping. The patch clamping technique can record the opening and dosing of a single ion channel. With a technique called patch clamping, developed in the 1980s by Bert Sackman and Erwin Nair, neurobiologists can record currents caused by the openings and closings of single ion channels. Using a fine pipette and slight suction, patch clamping isolates a small patch of plasma membrane. Using the pipette as an electrode, voltage differences due to movements of ions through channels in the isolated patch can be recorded. Figure 11. Frequently, a patch will contain only 1 or a few ion channels. Thus, the electrical recording from that patch can show individual channels opening and closing. Sackman and Nair received the Nobel Prize in 1991. Action potentials can jump down axons. In vertebrate nervous systems, increasing the speed of action potentials by increasing the diameter of axons is not feasible because of the huge number of axons in these organisms. Each of our eyes, for example, has about 1 million axons extending from it. Evolution has increased action potential velocity in vertebrate axons in a way that does not require large size. When we described glial cells earlier in the chapter, we saw that certain glial cells wrap themselves around axons, covering them with concentric layers of myelin. See figure 3. These myelin wrappings are not continuous along the length of the axon, but have regularly spaced gaps, called nodes of Ranvier, where the axon is not covered. Figure 12. Myelin electrically insulates the axon, that is, charged ions cannot cross the regions of the plasma membrane that are wrapped in myelin. Additionally, ion channels are clustered at the nodes of Ranvier. Thus, an axon can fire an action potential only at a node, and that action potential cannot be propagated through the adjacent patch of membrane covered with myelin. The positive charges that flow into the axon at the node, however, spread down the inside of the axon. When the spread of current causes the plasma membrane of the next node to depolarize to threshold, an action potential is fired at that node. Action potentials therefore appear to jump from node to node down the axon. The speed of conduction is increased in these myelin-wrapped axons because electric current flows very fast through the cytoplasm in comparison to the time required for channels to open and close. This form of impulse propagation is called saltatory jumping. Conduction is much quicker than continuous propagation of action potentials down an unmyelinated axon. Neurons, synapses, and communication. The most remarkable abilities of nervous systems stem from interactions among neurons. It is these interactions that process and integrate information. Our nervous systems can orchestrate complex behaviors, deal with complex concepts, and learn and remember because large numbers of neurons interact with one another. The mechanisms of these interactions depend on synapses between cells. Synapses, as we saw above, are structurally specialized junctions where one cell influences another cell directly through the transfer of an electrical or chemical message. The cell that sends the message runs the presynaptic cell, and the cell that receives it is the postsynaptic cell. The most common type of synapse in the nervous system is a chemical synapse, one in which chemical message released by a presynaptic cell induce changes in a postsynaptic cell. Institute for Advanced Studies, Jodhpur 43. Unit 7 System Physiology Animal. Comma. Tilde. At each axon terminal is an enlarged knob or button-like structure that contains many vesicles filled with neurotransmitters. The neurotransmitter used by all vertebrate motor neurons is acetylcholine. The portion of the axon terminal plasma membrane that forms a synapse with a muscle cell is called the presynaptic membrane. Acetylcholine 1 is released by exocytosis when the membrane of a vesicle fuses with the presynaptic membrane. Where does the neurotransmitter come from? Some neurotransmitters, like acetylcholine, are synthesized in the axon terminal and packaged in vesicles. The enzymes required for acetylcholine biosynthesis, however, are produced in the cell body of the motor neuron and are transported down the axon to the terminals along microtubules. Other kinds of neurotransmitters, such as peptide neurotransmitters, are produced in the cell body and transported down the axon to the terminals. The postsynaptic membrane of the neuromuscular junction is a modified part of the muscle cell plasma membrane called the motor end plate. The space between the presynaptic membrane and the postsynaptic membrane is called the synaptic cleft. In chemical synapses, the synaptic cleft is, on average, about 2040 nanometers wide. Neurotransmitter released into the cleft by the presynaptic cell diffuses across to the postsynaptic membrane. Figure 13. The motor end plate contains acetylcholine receptor proteins. These receptors are chemically gated channels that allow both Na and K to pass through. Since the resting membrane of the postsynaptic cell is already permeable to K, the major change that occurs when these channels open is the movement of Na into the cell. When a receptor binds acetylcholine, the pore of its channel opens and Na moves across the membrane, depolarizing the motor end plate. Figure 14. 44 Institute for Advanced Studies, Jodhpur. Unit 7 System Physiology Animal. Acetylcholine receptor is a chemically gated channel. The motor end plate